far as I know, it's like the immutable data structure. So you don't do any in-place updates for LSM trees. And LSM trees are better suited for SSDs, as far as I know. Okay.
Yeah, it is. It is better suited for SSDs.
Yeah. So yeah, we will be covering B trees here, which is the mutable ones. So we will be doing in-place updates for B trees. Okay, and there's one assumption here. So you will see in Postgres, for example, I have heard that there is like we maintain multiple versions for a key. But here, for simplicity, we will just assume that like one key is associated to one record. There is no version. This is an assumption that we are making, right? So yeah, traditional search trees like binary search trees, 2-3 trees, AVL trees. Why are these not good for usage in databases? I'm sure you guys know about BSTs, so I'll like okay. So the thing is, yeah, we have group node. It's a binary tree, so we just have two children for each node. And you can see, like, for example, take this node, and on the left side, you have like all the nodes are less than 5. You can see. So all the nodes which are less than 5 go to the left subtree, and all the nodes which are greater than 5 go to the right subtree. So this is shortly how uh, binary search trees work. And yeah, so there are a couple of problems with this. One thing is data locality, right? So in the old days, we didn't have SSDs. We used to have this spinning hard drives. And the problem is, let's say you are at this node and you are jumping to this one. Let's say this is node A and this is node B, and you don't know like what's the distance between these two nodes, like the physical distance. Like maybe the disk needs to spin 270 degrees to reach here, I don't know, or maybe 180 degrees to reach here. So what we want to achieve when we are talking about like storing things on the disk is that we want to do as less movement as possible. So we want the disk to spin as less as possible, and we want we want data locality. So we want most of the data to be as near to each other as possible, right? And so here you can see it's just complete madness, because let's say you're doing a traversal like this. You're going like 5, 2, 4, 3 like this. So you don't know like how far these nodes really are physically in the disk, and maybe the disk needs to spin too much to do this traversal, uh, which causes high search times. And there is a solution for this, like a temporary solution, which is basically paged binary search trees, uh, which they talk about here. Yeah, paged binary trees. Uh, where's the image? Yeah, this is the one. So you can see like you take a couple of nodes, let's say like 3 nodes, and 3 nodes are stored in a single page. You can see. So kind of like the disk needs to rotate less now. Okay? So before, let's say like 1 rotation, 2 rotation, and 3 rotation, if there was like 3 rotations, now with this like page sort of thing, with the paged binary search tree, we need to do like just 1 rotation, which is from here to here. Actually 2, like 1 to maybe like find this one. Once we find this one, then when we are going from here to here, we need to find this page as well. So we need to do uh, 2 disk rotations, which is kind of like an optimization. But this is a temporary solution, basically. Yeah, so this is about paged binary search trees. Okay. Next we have tree balancing. Yeah. So another problem with this binary search trees is that we can get a situation like this where basically it's getting kind of like a linked list and not like a tree. This is a name. The technical name is pathological tree, and you can see since this is kind of like a linked list, the search complexity is linear instead of logarithmic. So you go like one instead of uh, traversing like this, how you do in a tree. So we can have a situation like this as well, called a pathological tree. So the solution to avoid this kind of problem is called tree balancing. And yeah, you can see here. So every time we do an insertion, let's say we have like 5 and 3. Initially we have 5 and 3. And we put 2, right? So the condition we want to follow, first of all, let's define what is a balanced tree. What is a balanced tree? Let's define that. Uh, so a balanced tree is somewhat like this. So let's say we take this subtree, okay? The criteria for a balanced tree or a balanced binary tree is basically you take the left subtree, which is 2, 1, and you take the right subtree, which is 2, 3, okay? And you take the height difference between the left subtree and the right subtree, right? And the height difference should at max be 1. It can be 0, which means like the height of the left subtree and the right subtree are equal. Or let's say you put like a 0 here. Okay, so 2, 1, 0, and 2, 3. So then the difference between these left and right subtrees will be 1. So this will still be balanced. But let's say you do 2, 1, 0, and then minus 1. So the height of this left subtree is now 2, 1, 0, minus 1, which is 4. And this right one still is 2, 3, which is the height is still 2. So the height difference is 2, because of which the tree gets unbalanced. I think if I drew this somewhere, then it would have been much easier to explain. It would look much nicer. Okay, we can try that next time maybe, but let's just go like this for now. So yeah, the criteria basically is that the height difference between the left and the right subtree should not be more than 1. So every time we do insert, like if we have 5, 3, we insert 2, and then you can see this right subtree, the height is 3, the left one is just 1. So the difference between them is 2. And what we do is we pivot, right? So we have this 3, we make this, like we promote this to the root node, and we demote its parent, which is this one 5. We demote this to the lower level, basically. So this is and we do this for every insertion. Okay, so every time we insert, we check whether the tree is balanced or not, and we, if it is not, then we do this kind of pivot. So tree is balanced after each operation, and we do a rotation step after nodes are added, or added or removed as well. Okay, so for adding or removing, in both the cases we do a balancing. If the insert operation leaves a branch unbalanced, yeah, so basically we rotate the middle round. Okay. And you can see the definition here for a balanced tree is the one that has height of log 2n, or in simple terms, difference in height between the two subtrees is not greater than 1. That's the simpler definition, basically. Yeah. So to avoid the situation, we need to do balancing. That is one thing. So balancing the tree, that's point one. And point two is to consider data locality, because we are storing the data structure on disk. So these are the 2 points that we need to think about. Right, so trees for disk-based storage. Okay, now here the author speaks about the solution. So you can see, so for example, with binary search trees or 2-3 trees, the thing is, the number of children for a node, let's say like 4, the number of children is 2 here. And in fact, for every node, the number of children is 2. For 2-3 trees as well, what's the children? Does anybody know? No? We can search. Is it 2 children and 1 data element, or 3 children? So okay, at max like 3 children. And so it's kind of a binary tree as well, at most. Right. So the solution, basically the problem is the number of maximum children that we can have. So here you can see the maximum is 2 for item 3. And what if we increase the number of child numbers? What if we increase from 2 to, let's say, 10 or 20? So this property, basically, how many children, what's the maximum number of children that a node can have? That is called a fan out, right? So the binary tree has basically a fan out of 2, because we can have at max 2 children. So you can see, due to a low fan out, this is the maximum allowed number of children per node. We have to perform balancing. I talked about this. Relocation of nodes. This is something. So this is about data locality, basically. And we have update pointers rather frequently. Okay, yeah. So when you're doing tree balancing, you need to update pointers as well, right? Like, let's say we have like a, yeah, so this pointer you can see. And when like this kind of pivoting, let's say this is only a subtree and there is a parent, maybe you need to do pivoting there as well. You know? So this can recursively bubble up, and you need to do pointer changes basically. Okay, let me just. Yeah, and also another thing here is that since we will be storing this thing, or rather this thing, on the disk and not on the memory, when this thing is in memory, you can directly point to a memory location, right? Like this one has 0x00A or something. So this directly points to a memory location. But when you're on disk, you cannot, like, there is no concept of pointing to a memory location. So you need to consider that as well, okay? So what we do is actually we take this pointer and we kind of like pre-compute the storage location where this node is stored, right? So there is an overhead there as well. In that, like, if we do, pointer changes, then we need to compute the storage location again, right? So in memory, this is directly, okay, you have the memory address and you directly point to this memory address. But in disk, keep in mind that it doesn't work like that, because there is no concept of like memory address there. And what we need to do is, when we are flushing to the disk or when we are saving this thing to the disk, we pre-compute this pointer basically we compute this pointer to the disk location, right? And we will be talking about like the structure of a disk and the units in which we do read and write. So we will expand more on that later. Right.
Yeah.
So
we go to sorted tables also.
what?
Like how each node in the B tree will be stored on the disk. Did you go to also?
Wait, your voice is pretty low.
Can you hear me?
Still, it's low.
It's still low.
Okay. It has to chat out.
Or you can just type
Uh,
maybe. I don't know in the chat
Yeah,
room.
yeah.
That would be easy.
Give me 2 seconds.
By the way, am I going too fast or? Wait, when you type. Mm-hmm.
PC is fine.
Check the chat.
Asking how will B-tree be stored on disk? Have you gone through slotted pages for storing B-tree nodes on disk? What is slotted pages? Is it the paged B-trees? Oh, okay, no, slotted pages for. We didn't even arrive till B-trees right now. We're still talking about binary search trees. I remember somewhere the author talks about slotted pages. It says a node is serialized to bytes to be stored on disk. I exactly don't remember this slotted pages thing, but I remember that I've seen somewhere this thing in the book. Okay, yeah, sure. Yeah, sure.
Yeah, sorry to disturb, man. Okay.
Okay, yeah. So I'll continue. Yeah, so basically the thing is this fan out, which is the maximum number of children that a node can have, right? And what if we increase the fan out and see what like changes we have because of that, right? By the way, I will again summarize the problems. So one is basically this like pathological tree because of which we need to balance, right? We need to balance the tree every time we insert something or every time we remove something. That is number one. Number two is basically, yeah, so when we are balancing, you can see we do some pointer updates here, and the pointers don't work as simple as they do in case of RAM, main memory, because we need to pre-compute this pointer stuff and get the storage location. So it's a little bit complicated on this. So we don't want to do too much of this balancing operation. Like we want to decrease this pivoting operation as much as possible. So we need to do like as less pointer updates as possible, right? So that's with the balancing to avoid this kind of situation. And another thing is data locality, right? So these are the two problems that we have, kind of like three problems with the, like we don't want to do too much of your updates. So kind of those are the three problems that we have, and the solution that's suggested is having a high fan load. So having more number of children for a node. Right. So naive on disk BST, this binary search tree implementation, would require as many disk seeks as comparisons, since there is no built-in concept of locality. Yeah, so as I told you, basically for B trees, we need to do like, okay, you do this kind of traversal. Let's get it. Yeah, you do this kind of traversal. So the disk maybe needs to rotate like 5 times, right? Once for finding this one, then here, like 1, 2, 3, 4. Okay, 4 times. The disk needs to rotate 4 times if you do this traversal, right? So and if these are located far apart, then the disk needs to rotate significantly, which will take good amount of time. So considering these factors, version of the tree that would be better suited for this implementation has to exhibit the following properties. So one thing is high fan-out, so basically increasing the number of maximum children that a node can have. And another thing is low height to reduce the number of seeks during traversal. Yeah, so what that says is like we want to decrease the height of the tree, so we don't need to do like too much traversals, like too much traversal from one level to another level. So the less number of levels we have, the less traversals we need to do. So the disk will rotate less. Basically, that's the concept. So yeah, these are the two requirements: high fan-out and low height. And it turns out that these two are actually related. Okay, it's like an inverse relation. Yeah, here you can see fan-out and height are inversely correlated, right? So we will see that when we have a high fan-out, automatically we get a low height for the tree. Now we transition to disk-based structures, so the B tree thing. Okay, first we actually talk a little bit about hard disk drives and SSDs. Yeah, so I got to know this when I was implementing file system drive for my OS, and the thing is basically you cannot read like 1 bit or 1 byte like that from a disk. Okay. There is a smallest unit of transfer, and this is called a sector, and the one sector can range like from like 512 bytes to 4 kilobytes, right? So let's say you try to read from a location on the disk, right? So you cannot read, like let's say you want to read 4. Okay. So when you want to read 4 bytes, actually one sector gets fetched, right? So if the sector says it's 4 KB, that means you're actually doing a fetch of 4 KB, right? Which has quite good amount of overhead. So you need to keep that in mind, right? So smallest transfer unit of a spinning drive is a sector. The size can typically range from 512 bytes to 4 kilobytes. And head positioning is the most expensive part of an operation on the HDD. So basically, finding the sector is the most expensive operation because the disk needs to rotate and needs to find the sector. And once you find the sector, you can fetch. And then when you fetch the sector and you're reading inside the sector, let's say, that's easy because you have fetched the sector and loaded it in memory, and then you're just reading like contiguous data, basically. So you can see here, this is called sequential I/O, and inside a sector, when we read, it's sequential I/O. So it's like we load the sector in memory, it has got low overhead. So this is the only thing about hard disk drives. Okay, so the most expensive operation is finding the sector, and then reading stuff from inside the sector is called sequential I/O, which is cheap. And next we have solid state drives, which is not like necessary in this chapter, but when you read about LSM trees, then this thing comes into play, and why we need something like LSM trees, which is optimized for SSDs. So if you get to know the structure of SSDs, you will realize that why we need LSM trees and why basically these. You remember in the beginning we talked about this. So storage engines, we have two types, mutable ones and immutable ones. Okay, and why for SSDs immutable storage engines are kind of more optimized, right? And not the mutable ones. B trees are mutable. So yeah, this is kind of the hierarchy that we have in an SSD. We have like die. Inside the die we have planes. Inside planes we have blocks. Inside blocks we have pages. Inside pages we have arrays. Inside arrays we have strings. Inside that we have the fundamental unit, which is memory cells. Okay, and the thing is, we have these pages that you see. What happens is, okay, blocks typically contain these many pages, so you can see blocks contain pages, and yeah, so the smallest unit that you can read or write is a page, basically. Okay, and we can make changes to empty memory cells. Smallest erase entity is not a page but a block. Yeah. So basically, what happens is in SSDs we have something called garbage collection, right? Something called garbage collection. So let's say we have like 64 pages here, and only 2 pages have data in them. Okay. So what happens is basically these like data from these 2 pages are moved to somewhere else, like let's say here, and then this whole block is erased. Okay, so the whole block is erased means like data is erased from these 2 pages, and then you can write data here. That's how it works basically. It's hard to explain in this meeting. Like currently, best thing would be there is a very nice lecture from Hussein Nasser.
When would we consider that the garbage collection is triggered though? Because if we say a block is an arbitrary amount of pages, what's the starting point for the garbage collector to say just clear a block and transfer it to another block?
Okay. Yeah, it's explained here. Wait. It's called the flash translation layer. Okay, yeah. Actually, it's pretty complex how SSDs work, and there's a lot going on here. This page you can see this page there's kind of a map that is maintained in SSDs. Okay, so you have kind of a map, and we map each page to some kind of address. So
Sort of like a bitmap.
Yeah. So you can see we have a component called flash memory controller, and this is mapping the page IDs to their physical locations, and it's also tracking empty, written, and discarded pages. And then we have the flash translation layer. Okay, so this is basically doing like erasing of blocks. Remember, we can, like it's written here, you can see, we can erase a whole block, like we cannot erase individual pages, you know. So let's say
Okay.
like if you have like you have this block, okay, and you have like 64 pages in here, and only 2 pages are there where actual data lives, and remaining pages have like garbage data, you know. And then the garbage collection will trigger because like only 2 pages have actual data. It's very low. So why not just free the whole block? There is some advantage to that. I forgot what it is. But basically, the garbage collector, what it will do is it will apply a kind of like a high voltage to
Mm.
these 2 pages. Like it will move the data from here to here, okay, and then it will erase the data here.
Got it.
So you have a completely free block, like block with all the
It is
free.
some form of compaction.
Yeah.
Okay. And how does it know when some like a page has garbage data? Like, how does it realize that? How does it make out the difference between
You can see
doing
it
normal?
like tracks, tracking empty, written, and discarded pages. So this
Okay.
component, which is flash memory controller, it keeps track of all those things.
Good.
So okay, yeah, I mean it's I don't want to speak about this in detail. I also like forgot kind of the full details, but this guy Hussein Nasser, I don't remember where is that limitations? Maybe this one.
I think I talked about the limitation.
Yeah.
Yeah, this one. This one is very good.
Yeah. This is the one. I'll just send the link of this.
I think it's, as I understand, it's similar to how the operating system handles virtual memory and the pages. Uh, I think SSD just has blocks as a higher level abstraction over pages. That
Yeah, exactly. There is some kind of thing similar to paging going on as well.
yeah
Because you can see like these pages, as I told, like if we have like 2 pages here which have data,
yeah
and then they get moved here, and then there is a mapping as well, like the page ID to physical location mapping, and we need to update those mappings as well. Yeah, I mean, so you guys can watch this video in detail. He speaks like he explains it very nicely. Uh, he gives a very nice overview. So yeah, that is the thing, and I guess we can I can maybe go in detail when we talk about LSM trees someday later. But for now, this is not being used in the current chapter. Okay, so okay. Yeah, and so okay, one thing is both in case of hard disk drives, you can see we read and write in terms of sector, and in case of solid state drives, we read and write in terms of pages. So the OS has some kind of abstraction, like abstraction API, uh, which is common to both SSDs and HDDs. So uh, where is it written? Most operating systems, yeah, have a block device abstraction. So it's kind of like you can imagine like this is for like we already have blocks here, but yeah, it's like you can consider these as blocks. Okay, so these are the units of transfer, units of read and write. When we read one page. When we write one page. Okay. And yeah, this is also one thing, by the way, this buffering. So you will see DBs have like a wall component as well, which is write ahead log. So when you write something, okay, to the database, then it doesn't immediately get flushed to the disk. Okay, it still like remains cached in memory. Okay, so let's say you write, like you insert a user in a database. Okay, there is no guarantee that the user has been like written to the disk. The only guarantee that the database gives you is that there is a wall, which is like a log. So if you don't know, this is a very like basic thing, and most of you guys should know by the way.
Write ahead logging.
And yeah, write ahead logging basically, and it's kind of like an entry that okay, this user gets inserted into this table, right? So we have that kind of entry that's immediately written to the disk. Okay, that's immediately written to the disk, but the actual entry is not immediately written to the disk, and it's cached in memory, and then like when the cache fills up, we flush the cache to the disk. Okay, so that's how.
I think it uses fsync. So there are other
Yeah.
times when you try to write to the file to the disk. So operating system has its own like does something more like it buffers your writes on its own for efficiency's sake. But for write ahead logging, I think they use fsync mode with the file so that when you do write it to disk, it immediately gets written to disk. It doesn't
Yeah,
get buffered in any way. So you don't
Yeah.
lose because write-ahead logging is mainly for durability's sake. So if in between anything that you're doing, if your database crashes, you wanna return it back to its last correct state. So if you're when you're writing the write-ahead log itself, you don't want to buffer it in any way. You don't want to lose your write-ahead log. That's why they use fsync.
exactly. So I mean, this buffering thing is built into the OS. When I was implementing this OS thing, if you've seen XV6 as well, you will see like the file system driver has an inbuilt cache. Okay, and when you try to write something, it first gets saved in like it first gets saved in the cache, and then it buffers it buffers in the cache, and then it basically flushes to the disk. And then you have, of course, in Linux you have the fsync system call. So you just say, hey, just like skip the caching and just directly write to the disk. So that is the thing. This is what buffering is. Okay, writing only full blocks and combining subsequent writes to the same block can help to reduce the number of required I/O operations. Yeah. So basically, by buffering, the intention is to lessen the number of I/O operations to the disk. I/O operations are a little bit expensive when you talk about HDDs, so that's why when you write, again, the disk needs to spin. On disk structures. So here basically the pointer thing that I was talking about. So because when you're having something in memory, then you can directly point to the memory address. But on disk, you don't have this concept of memory address, right? And you need to pre-compute the storage location or the disk location or like the block number basically. So because the disk is seen as a series of blocks, and you need to compute the block number from the pointer basically when you're saving this thing to the disk. Okay, so you can see most of the time on disk offsets are pre-computed in cases when the pointer is written on disk before the part it points to. are cached in memory until they're flushed on the disk. That's what basically it means. Okay. And yeah, of course, like this, when you're trying to do the balancing, as we saw here, uh, yeah, when you're trying to do this balancing, there are pointer updates, and then you need to compute the storage location again. So maintenance overhead from remapping these pointers as a result of balancing, and we want to decrease uh, these like the balancing operation as much as possible, so we don't need to have too much of pointer updates. Wait, can you give me like 3-4 minutes and I can install Discord on my iPad and I can like kind of draw, which will be easier as well because currently what I'm doing is I'm just talking and I think it's not a very good way of explaining something in a meeting. So give me 3-4 minutes. Let me just quickly install Discord.
Yeah, sure.
And okay, there was one guy who was saying about something like slotted pages. So yeah, man, you can speak about that in the meantime.
Sure. This the issue is that you haven't really introduced B trees yet, and that is like something that you talk about after you've explained what a B tree is. Or I could just explain B trees really quickly, like a refresher, talk about what it is,
Yeah,
and
sure,
then move to what I'm saying.
sure, yeah.
Okay. Okay. Cool. Uh, Let me just share my screen. Can you guys see my screen?
Yep, yeah.
Yeah, okay. He was talking about B trees. I know this is B plus tree, but I was going through it. So just yeah, a B tree is this to say it's essentially the same thing, but without these pointers that you're seeing. Just think about this. This if this is a B tree. So what I wanted to talk about is how each of these nodes. So you can see that let's say for this node is 400, 430, and 453. All of them belong to one node. So how would you serialize? So there is you can create a class like if you're writing Java, then you create a class which represents this node, right? But once you have to persist it on disk, how are you going to serialize that node into bytes so that you can write it to a file? Because a file is just a collection of bytes. So how are you going to serialize an in-memory object into a series of bytes that you can store on a file? So that is what I wanted to talk about. So one of the ways to do that is called slotted pages. Uh, so cool. So if you see here, let's say 400, 430, and 453. Let me just insert something in between. Let's say I do 412 and I insert. So you can see that I've inserted something in between 400 and 430, right? So there are let's just go through maybe two or a very primitive way of storing this on disk. Let me just share another part of my screen. Cool. Yeah. So like if you saw the B tree, whatever I showed on the B tree, so it's just each node is just a left pointer, a key value, and then a right pointer, then another key value, then another pointer, right? So it's like that. So the most basic way to do it would probably be to just store all of this information serially. So you just what you do is so if there are three children and there are two key value pairs in between those three children, then you would just do zeroth pointer key value, first pointer key value like that, and you just store it you just serialize it sequentially. The issue with that is, let's say I want to insert something in between. Like if I want to insert a key value pair in between, then I'd have to basically everything, all the elements before the after that have to be rewritten, right? Like for example, if you can see here, let's say I want to insert something in between cell 1 and cell 2, then everything from cell 2 till cell n has to be rewritten. Basically, the like an array, right? If you want to insert something in the middle of an array, like in the middle of a position somewhere, then you would have to push all the elements ahead of that ahead of that position one element size to the front, right? Because you want to make up space. But the problem with that is you're rewriting a lot of the information. Does it show that the stream has ended? That's my thing.
No, I can still see your screen.
Okay. Yeah. So that's what. So the thing is, the most primitive way would be to just to store all the information like sequentially. You just store, let's say, pointer one, a key value, pointer two, key value, pointer three, like that. But the like the issue, like how what I was explaining was, let's say if you want to insert a value in between two key value pairs, then you'd have to just move everything to the front by some by some amount, which means you're rewriting a lot. So the way to fix that is called slotted pages. So what you do is within a node, you would store all the actual information on one side of the page, one side of the node, and the other side is just pointers to it. So let's say there's three cells, right? Let's say I want to insert a cell between cell 1 and cell 2. So it would be here somewhere. So all I would have to do is add the information here. Can you see you can see my mouse, right?
Yep.
Yeah. So you would only have to move pointer 2 and pointer 3 ahead, and then insert a pointer to the new object here. So you would have to insert a pointer here, and pointer 2 and pointer 3 would have to be moved by some fixed amount, and then the actual content can be put anywhere in this free space. The whole point of that is that you're rewriting a smaller amount of data. So pointer 2 and pointer 3, they're just pointers to they're just offsets to the actual information. So you're essentially rewriting much smaller amounts of data. So if all of this, so let's say in this case, this is the primitive way to do it. If you had to insert something between cell 1 and cell 2, then you would have to write cell 2, you'd have to shift everything forward by some amount of space, right? So you're rewriting all of the information again. Instead of doing that, why not have pointers to that information and then insert only the pointer here? So then you'd only be rewriting the pointer 2 and pointer 3 ahead.
I understood. I think I have read this before as well. So basically, the concept is the actual keys are cells here, right? And we don't care about the ordering of the cells. We don't care about the ordering of the cells, and we just do appends for cells. But then at the end, we maintain the pointers, and we maintain order of these pointers.
The pointers, yes,
and
exactly. So
and the overhead is also very low for rearranging the pointers because the memory they occupy is very low. So.
They're small. They're just offsets, right? So they're like integers, like int32 you could say. So each one of them is much smaller than the actual. So the key and the value, you have no control over what the actual size of the key and the value can be. So it's a much higher overhead to rewrite key value pairs every single time. So it's better to not rewrite the key value pairs, but to rewrite or to push the pointers to those key value pairs ahead, and then make space. I should have had a visualization ready, but it was on short notice.
I have one question.
Yeah.
Okay. So my question was that so there for SSD or hard disks or whatever it is, if the memory if the storage is sequential, if the read is sequential, then it's going to be much faster than if it's according to the pointer I have to jump across the different part of the disk. So doesn't make it slower?
Yeah, no. This page.
No. This is a single page.
This page. So I'll answer that. There's whatever you're seeing here, this entire thing fits within a block on the disk. So you're not jumping between blocks on a disk. This entire thing fits in a single block. So when you're reading from the disk, you read the entire thing.
Okay, okay.
Does that answer, or you have
Yeah.
any
Good.
follow-up questions?
Okay, it answers. Okay.
So depending, so it's how you want to map it. If you want each of these, so this is a page. This is a logical page that you come up with. You can set the size of this page. So let's say a block on the disk is 512 KB. Then you can say that each page, each of these structures is 4 KB. So then you could fit how many 512 by 4 of these pages. So when you read, as you have to you make sure that since you're like you're choosing the size to be divisible by 4, that you would be able to read the entire thing. So you're not going to read parts of it from one block and
Okay.
cool. Yeah,
Uh,
doesn't make too much
so that
sense
is
now because the
yeah, yeah,
ending is supposed to be in the end of the B tree. But okay, sorry.
yeah, that's fine. Um, okay, one thing is that can we can we move to Google Meet, please? Because in Discord I cannot join from two devices, and from iPad I cannot present with like share my screen. Can we rather move to Google Meet because we can do that there?
Sure.
And the link,
Okay.
and we'll
Hey, if you don't mind, just give me 2 seconds. I found a much better picture. I'll just take 2 seconds to just show it. It'll be much
Hmm.
better.
Yeah.
Yeah, can you see this? I think this is much better because it tells exactly what is in each slot and right. So if you see each node, each B tree node is going to have two things. It's going to have key value pairs and it's going to have pointers to the child nodes, right? So we don't want to be writing these. We don't want to be writing key three value three, key two value two. We don't want to rewrite them again and again. We want to just be able to move the slots around. So let's say I have to insert a new key value pair in between. Then instead I can just move these two slots in front, and I
Hmm.
can put one slot here. And the pointer, I can point it here. So it doesn't really matter exactly where the actual data is within the page. Only the slots are important. The ordering of the slots is what we maintain. It doesn't matter where the actual data is. We just point to it.
Yeah. And this
That's
whole thing is in like a disk fits in a disk block basically.
Yeah, so that depends on what you want the size of a page to be. If a disk block is 512, you can choose to make. Once you explain B trees, you will see that after a certain point, we want to split the node. Like for example, if a node is supposed to have a maximum of 4 items,
Yeah.
and you
Hmm.
add a fifth item, we split, right? So
Mhm.
so let's say we have 4 KB pages, and each node fits in a 4 KB page. Let's say
Hmm.
we want to add another item here, but there's not enough free space. So that is when you would trigger a split of the B tree knot.
What kind of so okay, if I want to do a split or merge, then what kind of overhead is there for this thing? It's the same, I guess, right? Like
Yeah, I think merging is the same. It's like merging two sorted lists, right? You'd start with this, and you would start with this first slot here and the first slot of the other tree, and you just merge them, pick the smaller one and add it. Now the whole point is you don't want to be rewriting this data, which could potentially be really large. You don't want to keep rewriting it. You just want to be able to move this any the slots forward without touching any of this.
okay.
That is the whole point of this data structure.
Okay. Okay, I will go back to the B-tree chapter in the book. Wait. Okay, you'll see I will have two screens now. One yeah, one of the book and then one of this iPad. So I guess you guys can pin the both of them.
I can see the book only.
With this one. Yeah, okay, now it's good.
Yeah.
So I mean, yeah, we can pin both of these. Anyways, yeah. Okay, so the things we discussed till now. Okay. Yeah, the problems with BST or any like variation of binary trees is that one is we need balancing. So we don't get like this kind of linked list. That is one thing. And how we do this balancing? So we have a process called pivot or pivoting, right? So actually, it's like this, right? You have this kind of thing, which is kind of a linked list, and then we go from here to here. And this has got an overhead. And the overhead is basically pointer updates. Right? And we want to do as less pointer updates as possible because of that pre-compute thing that I explained. So this is number one, balancing, and number two is data locality. Right? And what is the solution? Solution is basically, so we saw something called fan out. Fan out is basically we have any node, pick any node, and what is the maximum number of children it can have. For B trees, of course, it is 2, and we want to increase this fan out to 10, 20, something like that. Okay, so basically we want to increase the number of maximum children. Right. So, and we saw that this fan out is also inversely proportional to the height of the tree. Okay. And the thing is, if we increase the fan out, the height basically decreases. Okay. This decreases, and the benefit of this is, so benefit of decreased height. Yeah, so let's say we are doing a traversal like this, right? So first we find the root node, that's 1. Then we go here, 2, 3, 4, right? So you can see we do like four times the disk needs to spin. So 4 times, possibly we need to fetch 4 slots from the disk, right? And the thing is, less is the height. So less is the height, less is the number of seeks, right? Or like the number of times we need to fetch from the disk, right? So this is a solution, basically having a high fan out, right? Okay. So yeah, here you can see so this is where B trees get introduced. B trees combine these ideas. So one is increasing the node fan out and reducing the tree height, which is basically like these two are related. So if you increase node fan out, automatically the tree height decreases. The number of node pointers, reduce the number of node pointers and the frequency of balancing operations. Yeah, so basically this pointer updates, we want to make it as less as possible. Okay, paged binary trees, I have already told about these. Yeah, so whoever is what it was, who showed the slotted pages thing. So basically you showed like B plus trees, and what the author has told here is that like B trees is like you can have multiple types of B trees, and the most commonly used B type is basically B plus tree, which is used in SQLite as well, and maybe in Postgres and these types of SQL as well. So that's why generally by B tree we mean actually B plus trees. Okay, so it's written over here, and in general these kinds of things where like binary search trees or B trees, where basically we have the nodes in an ordered manner, right? So suppose this is A, and then here like we have the children. And basically, if these things are in an ordered manner, then the tree in general is called ordered tree, okay? So B tree is an ordered tree, basically. Okay. And okay, now this is the thing. So first let's consider a binary tree, okay? So in binary tree, let's suppose this is the parent node A, and then we have B and C. So you can see we have how many keys are there in A? There's only 1 key, and then we have 2 pointers, basically. Okay, and this same concept is extended to the B trees, right? So in B trees, we have like this. So we have multiple keys. Let's say 1, 2, 3, 4. Okay, so 1, 2, 3, 4, 5, 6. So we have 6 keys, and we have 7 pointers, basically. Okay, just a simple example to help you visualize how B trees look. Suppose this is the root node, right? And we have 3 keys. Let's say we want to store the names of students, right? So what we do is, suppose this key. So this key we have from A to M, let's say. This one we have from M to, let's say, S, and this one we have from S to Z. Okay. This is pointer 1, pointer 2, pointer 3, pointer 4. So like we have 3 keys here. So we will have 3 plus 1, which is 4 pointers. Okay. So actually what happens is here we have M, here we have S. Wait a second. Okay, I have messed up a bit here. You know, this is wrong. Okay, let me try again. Let's say this is M and this is S. So we have 2 keys now. And we have 3 pointers, basically. So here we have this. Here we have basically all the names whose initials range from A to M, right? Then here we have all the names whose initials range from M to S. And then here we have all the names whose initials range from S to Z. Okay, so we have like 2 keys and we have 2 plus 1, which is 3 pointers. So this is kind of what the B tree structure looks like. Okay, so then you can break this, suppose this one, we can break this down further as well, right? So let's say this one is suppose M element O P, yeah, so let's say M and P, right? So we can, again, we will have like 3 pointers here, and here we have from M to from basically yeah, M to P, I guess, right? I'm a little bit confused now here. I guess you do actually LM, okay, you do O and P, right? So you have from M to O, and then here you have from O to P, and then here you have from P to S. And then you can break this down as well, this like this, and then at some point you reach the leaf nodes. Okay, so this is how kind of the structure of a B tree is, and you can see definitely there is some range thing going on. Okay, so let's say if you try to do a query like give me all the names whose initials range from A to M, right? So these kinds of range queries can be done very easily for B trees, basically. And when we study LSM trees, it turns out that these range queries are not that easy to do in case of LSM trees, but in B trees these things can be done very easily, and that's why you will see these like SQL, PostgreSQL. They are very good with the range queries because of this data structure, because like how B trees are. Okay. So now in this diagram we have 3 types of nodes, right? This is which is the root. Yeah, this is the root. Okay, this is the root. These ones that you see, like let's say this one is called an internal node, and then so we reach the leaf. Let's say this one. This one is the leaf node. Okay, and there are some terminologies. One thing is like the order, and one thing is the degree. Okay, of a B tree. So as far as I know, degree is the maximum number of children that you can have and order is the minimum number of children that you can have for a node. Let me just verify that. Wait. So order and degree of B tree. Okay, degree represents the lower bound. So I flipped this. This is the max, and this is the min. Okay, I'll share the link here in Discord. Right. Okay. Now this example that I gave, let's say the order is 3. Okay. So maximum we can have 3 children, right? So let's say this one, this P2S, or this one. This is a leaf node. This M2O. This is a leaf node. So we won't be having any children here. Yeah. And let's say we have like wait. We have we can have at max 3 children here, right? Or 3 keys here. So like let's say M1, M2, and M3. These are the student names, and I'm just using some kind of variable. M1, M2, M3. These are the student names in this leaf node. And now let's say you try to insert M4, right? So when you try to do insert M4, you can see we can have at max 3 keys, and you're trying to insert a 4th key here. So what we need to do is split up this node into 2, right? Okay, I will go back to the book a little bit, but this is what the structure of a B tree looks like. If you try to read from the book, it will, I mean, reading in text, it's a little bit like confusing, okay? And having a diagram, I think, always helps. So this is kind of what B tree looks like. Just the important thing is this range, okay? Because of this, we can do like range queries very easily with B trees. That's the most important part. Okay. So, okay, also, definitely another thing is, so these keys that you see here, this M1, M2, and M3, these are sorted, by the way, okay? So that's why you see we have from A to M, and then here we have from M to S, here we have from S to Z, like that, okay? So the keys should be sorted. So let's say here, in this one, if we want to do a lookup among the keys, we can do a binary search, right? And we can have like a logarithmic search complexity, basically, right? So that's why we want to have the keys sorted in a node. So keys inside the B tree nodes are sorted in order, and because of that, we can use binary search to locate a key in a node, basically. Okay. And yeah, so here it says that, okay, because we are storing multiple keys in a node, so we have a high fan out, and I told you that if we have a high fan out, then we will have a low height, and because of the low height, now we need to do less jump from one level to another, right? We need to do less jump. Maybe the similar kind of thing if you were using a binary search tree, it would be kind of madness. There would be a lot more levels, right? Like maybe it would be like, okay, A to Z, this is the root node, and then here you would have maybe like A to M, and then here you would have like A to E, and then E to M, and then here again E to H, and then H to M, like that. So I mean, you can, and then here you have again, because you can have only at max 2 nodes, so that's why you can see the number of levels is increasing, and there are a lot of levels basically, and then for each jump from one level to the next, you need to do like a disk rotate basically. So is the disk, and you need to rotate the disk every time most probably you jump from one level to another. So that has got quite a good amount of overhead, and that's why here it's optimized. We don't need to do much of jumps because the tree height is low, right? Okay, and this I have already told, so we can execute both point and range queries effectively, efficiently, right? Okay, yeah, so we have, I have already shown in the diagram, this is kind of a mess, the diagram is a kind of mess now, but we have 3 kinds of nodes. One is the root, which stays at the top, and then we have the internal ones, where we don't have data, but we have these ranges, right? So you can see we have this M to S, we have S to Z, we store ranges here, okay? And then at the leaf node, we store the actual data, which is these names like M1, M2, M3. These are the names. So these are leaf nodes where we store the actual data. And this is why also B trees are built from bottom to top, okay? Built bottom to top in case of B trees or B plus trees. This is, if you guys have done Merkle trees, it's the same. Like Merkle trees are also built from bottom to top. And similarly, we have B plus trees, which are built from bottom to top. And this will be more prominent when we speak about like splitting and merging in a B tree, basically. Right, so these are the 3 nodes that we have: root node, leaf node, and internal node. Okay, this is the diagram. You can see this is how it looks. B trees are a page organization technique. We often use terms node and page interchangeably. Yeah, so basically like this, generally this one node and one page is kind of used interchangeably, and that's what it is saying. Roughly, we try to keep, if you see most of the implementations, we try to keep one node. Yeah, I mean, one node is equal kind of like one page, okay? Okay, relation between the node capacity and the, okay, now we have something called occupancy. Right, so consider this. Okay, are you guys listening, and is everything clear, or do I need to pace down or pace up, or what is it? Is everything fine? Yeah? Okay.
It's fine.
Okay. Okay, let me quickly draw a B tree again. So M and S. And then here, suppose we have like, yeah, so here we store A to M, we store M to S, and here we store S to Z. And let's say this is P and O, okay, O and P, and then here we have M to O, here we have O to P, and then here we have P to S, right? And the order is order, right? Yeah. The order is 3. So we can have 3 children at max, and this is a leaf node. And then here we have names, let's say like M1 and M2, right? And this one is empty. We don't have here. This one is empty. So there is a technical term called occupancy, and this is basically, in this case, it's basically 2 by 3, right? So the number of keys which are occupied or getting used, and the order, right? So I mean, two keys out of 3 are occupied. That is basically the definition of occupancy. And why we are talking about this? Because it can happen that the occupancy of the B tree tells us about how much space we are using. Okay, because let's say we have the root node here, and then we insert M1 and M2, and this is kind of what the B tree looks like. We don't have anything else, we just have M1 and we just have M2. Okay, so this internal node is having, like, of course it is having its storage allocated, but it's not used, it's just empty. This one is also having its storage allocated, it's not used, it's empty. This one same, this one same. The only 2 keys are being used here, okay? And all the other storage which is allocated, they are not currently being used, they're empty, there are no keys there. And kind of I'm wrong, because if that's the case, then what will happen is, let's say like this one, and this one will get merged actually together, okay? So it will get merged into one single leaf node, which ranges from O to S, right? But still the storage for this will be unused, basically, right? And this is one thing. So you can see here somewhere written that, yeah, so the tree storage utilization can get as low as 50%, basically. As low as 50%, because I mean, we can have this kind of situation. Let's say MS, A to M, M to S, S to Z, and we have inserted some stuff, let's say here. Okay, I actually forgot the reason why it can get like 50% is the term written here, but I read something, I forgot it now. Okay. But yeah, so basically this is the thing, like occupancy tells us about how much B tree current, like how much storage that is allocated for the B tree, how much we're using from that allocated storage. And it can get low in these kinds of scenarios. And if it gets low, it will basically trigger a merge of the nodes, basically, which we will study later. Okay, and yeah, the diagram that you showed, the guy who is showing the slotted pages diagram, he had something like this. Like this is, I'll just change the pen color. This is one leaf node, and this is another leaf node 2, and this is another leaf node 3. And sometimes what we do is we have like arrows like this, okay? And we connect the leaf nodes like this. So let's say we are doing some kind of range query, like A to S. So we start from here, we do M1, M2, this, suppose we have M3 here, and then we have O1 here. So we don't need to travel back to the parent and come here. We can just directly jump from here to here. So that's why sometimes we have these leaf nodes connected, or siblings connected with pointers. So when we are doing a range query, we can just directly jump from here to here, right? And we don't need to go back to the parent or something, which makes the flow more complicated. So this one is more easier. Okay, so it's kind of like a doubly linked list, yeah. Okay. Yeah, so this speaks about the B-tree lookup complexity. And okay, now the thing is, suppose we have a binary tree, okay? We are at the root node, and suppose we want to get to this node, right? When we go from A to B, when we jump from here to here, we kind of eliminate the possibility to explore this subtree, okay? So our search scope kind of gets halved, right? So when we are here, we have n nodes to search. When we jump from A to B, then we kind of have like n like half the nodes, like n by 2 nodes to search, right? Then when we jump from here to here, we have like n by 4. Actually, we are already at the destination, so this should be 1. But yeah, so you can see every time we jump from level 1 to level 2 and then level 3, our search scope gets halved. Search scope gets halved, okay? And that's why the search complexity is basically log 2n, okay? So what this means is, like, every time we jump from one level to another, our search scope gets halved. And in case of B trees, it will not be 2. It's the same kind of similar kind of concept, but it will not be 2. It will be k here, which is basically it's not properly explained here, but k is basically called a split factor, or is it explained here? Does anybody know about this properly? This thing, split factor, and the lookup complexity for B trees. But basically, split factor is this, okay? Like at max, how many children can we have for a node? So here the order is 3. So at max we can have 3 children. So k will be 3 here, right? And the lookup complexity will be log of 3. Most probably, okay? I can be wrong here a bit, because I am also a little bit confused, like where k is coming from, and this is, I was taking a look at this here. I can be wrong, but this supposedly is called the split factor, and this is like the order of the B tree. And every time, so okay, this is level 1. We have ms as a to z, and then here we have like a to m, we have m to s, and we have s to z, right? And when we go from this level to this level, these portions you can see are eliminated. So we kind of decrease our search scope. Like now the search scope is basically the initial by 3. That's what we do. And every time we jump from this level to this level, like from one level to another, we do this. We like it gets divided by 3, the search scope, and that's why we do this. Okay, log 3 of n. So instead of 3 children, if the order was k, that means we have like k children. So the complexity will get log base kn. Okay, so every time we jump from one, like this level to this level, search scope will be divided by k. So this is kind of the math that is going on. Okay, and if you try to read from the book, it's okay, but reading text is, I mean, it's a little bit confusing and takes time to understand. Okay, so yeah, you can see at most it's log k of n, basically. Okay, this part I skipped. I don't know what's written here. We will see. Okay, this is the lookup algorithm. See, the lookup algorithm, I don't have much to explain. It's very simple. Okay, like where is this? MS, and here you have A to M, you have M to S, S to Z. Again, here you do some kind of split, like M to O, O to P, P to S. So if you want to search, and then let's say here you have the leaf node, right? Like, I mean, actually this is the leaf node. This is the leaf node. Okay. So we have M1, M2, and let's say O1, like that. And if you want to search O of 1, O1, then you will, so okay, you are here at the first level, and you will just see, okay, M, is it, you will compare M and O. Okay, so L, M, N, O. So this, M is less than O, so you will go to here, right? And then again, you will compare M and O, and you will see, okay, M is less than O. So you will go here, like it will be O and P actually. This is the O and P. This is the one. So yeah, since it's O and P, this is the one, and then here you will go, and here, since this is a leaf node, you will just do a binary search, and you can find this key O1, and then you can say, okay, O1 exists, and let's say if you're searching for N2 or maybe element of PQ. Okay, if you're searching for Q, again the same kind of thing. You'll do like M is less than Q, so you'll go here, right? And then P is less than Q, so this time you'll go here, and then we don't have anything here, so you will just say, okay, this key doesn't exist. So this is how lookup is done. Okay. Am I going too fast, or you like it's fine, it's understandable?
This is understandable.
Okay, that's great. Right, so this is how lookup is done. Again, understanding with the diagram is much easier compared to reading this blob of text, basically. Yeah, so, and of course, the lookup complexity I have explained here already, O of log base kn. And then here, okay, you need to do a small binary search. Okay, so that will have, again, like it's again logarithmic, log 2 of the number of keys that will have, something like that. Okay, and range thing is just like range is, you can infer from here, right? Range scans also are pretty easy. Like you find the position of the first key, and then you go from here like this. So you go like in a continuous way, okay? Let's see, you want to do from M to, suppose here we have LMNO P, okay, like P1, and you can have a pointer here, as I told, here, like this. These siblings can be connected with pointer. So let's say you want to do a range scan from M to P. So you find the first node, which starts with M, and then you go in a contiguous way. That's how you can easily do range scans, right? So there's the lookup algorithm. Okay. And yeah, I mean, in SQL, you will also see that count thing, count something, you know. So that also you can do. You just go again in a contiguous way, and you count the number of keys that we have. Right. Okay. Okay, we have got 2 topics left. One is the splitting and one is merging. So we will talk about them now, and these are pretty important for B trees. So merging. Yeah. Okay. Again, what was this? MS. All right. MS. And then here you have A to M, M to S, and S to Z, right? And then here again, you have like M to O, right? And the order is 3, of course. So we can have at max 3 children. So we have M1, we have M2, and we have O1, okay? And let's say, now, okay, by the way, there is also another thing, which is insertion here, okay? And insertion is also similar, okay? Like, let's say if you want to insert M3, you look for M2, which is here, using this algorithm that I explained, using the lookup algorithm. You do lookup, and then this is a suitable position, so you insert here, okay? You just do like how you insert in a sorted array, similar way here you do the insert, okay? And then, okay, here, this slotted pages thing that the guy explained, so you can also follow that to do some kind of optimizations. So you don't need to like rearrange anything, okay? Or like you don't need to move O1 here by one place and then put M3 here. You don't need to do that. Wait a second. Okay. Right, merging. So yeah. So here we have this B tree. The order is 3. So at max we can have 3 keys here. And suppose now we want to insert M3. Okay. Now if we insert M3 here, it will be 4 keys, which we cannot have because at max we can have 3 keys. The order is 3. So what we do is we split this node. This is wrong. This should be splitting. We need to do splitting first. Yeah. So we split this further. So before this was leaf, and from leaf it will become internal node. Okay. Remember, like we have 3 types of node. I showed one is leaf. These are the internal ones that we have, and then we have the root, which is this one. So if you split this, so this will go away, and what we will have is, let's say, from M to N, and then from N to O. This is kind of what it is. So M to N, N to O. And then here we will have M1, M2, M3, right? So now it is satisfied. Now we have 3 keys, and then here we have O1, right? Just one. So this one you can see this was like leaf node before. This one it was leaf, but now it's not leaf. It doesn't contain the actual data, but it rather contains range keys. And this is an internal node now. And then inside, like we have the children are leaves basically. These are the leaf nodes now. Okay, and we have 3 here, 1 here, satisfying the order. So this is basically how we do the split. Okay, and by the way, this split can affect the parent nodes. Okay, it can bubble up to the root node actually. Okay, so let's say MNO we just have like we just have 3. Okay, suppose there is this kind of situation, A to D, and then D to like M maybe, and then M to Z, somewhat like this. This is one B3 node. This is internal. Okay, and then inside here we have 1 leaf node, 2 leaf node, and there's a 3rd leaf node. And all of these leaf nodes are full. Okay, all of these leaf nodes are full. And let's say now we want to, and suppose this is the parent, right? And now suppose we want to insert, like F3, something like that. So it will be here, right? Because it is D to M. So we need, because this is full, we don't have any space here. Like we already have 3 keys here. So this will split to 2, right? So we'll have something like this. So now we have like D to F, and then like F to M. And then again, let's say suppose you insert something, and you know we have got, when we keep inserting stuff in here, and then suppose we have 3 like let's say D2 F and F2 E F G H, and then H to M, and then this got full as well. And now we need to split further, and we need to have kind of another thing, another internal node. So then here you can see this thing here, we are having more than 3 now, you know, so like 1, 2, 3, and then this. So then we need to split this up as well, right? So you can see, first of all, we split somewhere here maybe, and then we need to split here. So it kind of bubbles up. I don't know whether I could explain this properly or not, but yeah, the summary is basically this split thing. It can happen like you start at the leaf node, but then it can affect the parent nodes as well. And in fact, it can affect the root node as well, okay? So in that case, when the root node splits up, like we have a new node here, and then here we have stuff. Okay, so let's say from A to M, and then like M to S, and S to Z, maybe something like that. I don't know, but yeah, this is the thing. Like the splitting can bubble up and affect the root as well. This was a little bit messy. The explanation was a little bit messy. I should have given more time to this. Okay. Yeah, this is the summary of how the node split is done. Let's just take this simple example, this one, right? So we had like M1, M2, O1, and then we split this into M1, M2, and just 1 space here for M3, and then here we had like O1, right? So you can see first we split, so of course we need to create this new node and allocate allocate storage for this new node, and then we need to copy this from here to here, right? So copy O1, and then once we have copied O1, we have an empty space, so it basically becomes this, and then we can insert M3 here, right? So these are the steps involved. So yeah, here you can see allocate a new node, copy half the elements from the splitting node. Okay, so this thing is called the splitting node, which is getting split basically. And this thing is called the new node. Okay, so we copy O1 from here, from the splitting node to the new node, and then we override O1 with M3 basically, and we get this kind of situation. Okay, this is one. So copy half the elements from the splitting node to the new one, and then place the new element into the new node, which is basically like place M3 here. It can be in the new node or it can be in the splitting node as well, okay? So if it is M3, let's say it goes here, but if it was something else, let's say if you're inserting O2, then it would have gone here, okay? So it depends what element you're inserting. It depends on that whether it will go on the splitting node or it will go on the new node, right? So it depends. And yeah, so here now we need to change the parent, like need to do some updates in the parent, because initially before the split it was what? M1, M2 and O1. So the range was let's say M2 P, some P element of P, yeah, okay, P, M2 P. And now that you have split this, now the range is somewhat like this, like we just have M1, M2, M3 here. So the range is M2O. By the way, this thing is exclusive, okay? So if you have M2O, this is exclusive. So O will not actually be here, but in the next sibling. So like O1, O2, so O2P. So you can see this, actually we have split the range into two, right? M2P is now split to M2O and O2P. And so this thing you need to update in the parent now basically, okay? So like, let's say this is the parent and we had a key here, which is M2P, and it just pointed to 1, and now this is the parent. Now it will be what? We will have like one extra here, right? So it will be M2O and O2P. This is the update that we need to do in the parent. And then we have like here, M2O, O2P, like this. So this is basically the thing, right? So these are the 4 steps. I hope you guys understood. So first we allocate a new node, we create a new node, and then we copy half the elements from the splitting node, which is this one. We copy from here to here, right? Copy half the elements, and then we place the new element. It can be in the splitting node or in the new node, it depends on the element, right? And then we update the parent. So we update the range in the parent, right? So we need to have like 2 keys now instead of 1, because we broke the range into 2 ranges, into 2 portions. That's right. So this is the splitting algorithm. Did you guys understand? Was it good? Like the explanation was fine, or it was just mess, or what?
I think B tree is done, right? Is there any more part to the B tree?
Yeah, just the merge part is remaining, but I guess we can skip that because I think guys can infer the merging part from that.
Okay.
If yeah.
Okay, so I think I should like continue for the.
Okay. But like, was a splitting thing like not you but the others? Can you say like, did you understand the splitting thing, and was it nice or what?
I think two other person left. The only Pranit is here.
Okay, no problem. Yeah, fine.
Uh,
Wait,
okay,
I
so
will.
like I thought like in the chapter like there would be a lot of content of the chapter, but most of the content is like uh, we know from the system design, but there's some good explanation from here and there. So
Okay.
so like I will go through the like
Okay, one thing is also that, one thing is also for the database internals book is it is kind of repetitive. Like it repeats the same thing again and again kind of. That's why I've
yeah
highlighted stuff.
yeah no I highlighted stuff too. So okay, I was sure to, but like I think like I tried to like summarize most of the thing. So like
Okay.
and like in a compact way, and like I'll go through the details in like in the voice. So
Okay.
we already know like what distributed system is. Is like there's like several
Hmm.
nodes, replicas, or different component like talking with each other and like trying to solve one problem but on multiple different replica at the same time. So but the concern about distributive algorithm is like the common problem that occurs in distributed system is that something like that system might not be reliable, like something on the system, or like there's might be some delay on the communication, there might be some reorder of the request that is coming, or the packet reordering, or there can be some failure to message delivery, or some of the
What
processor might
what do you
pause.
mean by
Yeah,
what do you mean by packet reordering or this request reordering? What
yeah,
is
yeah.
that?
So that is like that comes like later on the chapter, but so there's
Okay.
a like we already know like one of the like common what is the word uh, like there's only
Problem.
two hard problem in software engineering. One is cache invalidation, and two is naming things. So there's a
Yeah.
similar kind of talking on similar kind of saying in like distributed system, that is like there are only two hard problems in distributed system. Number two, exactly
Hmm.
once delivery, that is this is number two. Number one is
Hmm.
guaranteed order of messages, and number two again exactly once delivery. So
Okay.
it will come later. Okay.
Okay.
um, Starting. Okay, so where was I? Okay, so there are few problems. So slowing down, one of the components slowing down, and some of them might fail, crash, or go out of control, or suddenly
Mm.
I'm not sure like what they mean by go out of control. Maybe one of the failure model they are talking about that I will go briefly on later on the end. And some of them
Mm.
suddenly stop responding. So this is one of the two things, but you can think this is as like fault tolerance, like there can be some network partition, so some of the node
Mm.
cannot be reachable, so that can be one of the thing. Or they might be slowing down, like because of the processing is taking so long, they might be slow to response, or there
Okay.
can be some like out of memory thing happen and it can crash. So distributed algorithm, like there was some parallel he draw in the book about like how this is like similar to like even in the like in a single node too, like when because there's like multiple CPU core is running in parallel. So there need to be some data like locality constant, and there need to be some communication happen between them. There needs to be some like asynchronous or synchronous communication between them. So there's some small parallel he mentioned briefly talked about. Then after that there's like uh, four main concern about, not actually he didn't say main concern, but I'm saying so four concerns of distributed algorithm. So like coordination is that uh, like making multiple worker guiding, or like what is the word, orchestration is not the proper word, but like uh, it's like some sort of supervising like multiple workers at the same time. And cooperation is
Mm.
that multiple participate actually like working together to complete a task. And dissemination is like later part of the chapter, it comes later, like but entire chapter is for dissemination. But this is for this is about is like some message or some information like being distributed throughout all the nodes in a particular like cluster. This can be some distributed database system where some information is like distributed throughout the whole database. And consensus is the like this is achieving agreement or like coming to some everyone agreeing on like something, but like anonymously, sorry, not anonymously, like what is what this I forgot the word for it, but like everyone on the uh, everyone agrees on some on something, that is like the consensus. Okay.
Wait, just this dissemination, I missed it. What does
Yeah.
that mean?
Okay. Dissemination is like think like Cassandra. So some new message, sorry, something is being stored. So after like one of the node will get that information, so it will store that thing and it will like distribute or not distribute, like it will send the message to the other node so that it replicates that
Okay.
save the store that message. So dissemination is that like uh, spreading something across all the nodes. That is dissemination.
Okay.
Some information. Okay. So
Broadcast basically. Okay.
yeah, broadcast basically. Yeah, yeah.
To worker nodes. Okay.
Okay. So he briefly mentioned like the fallacies of distributed computing is like is a famous writing from the 1990s by Peter Deutsch or something, I'm not sure. So it's a like famous list of things like all the false assumptions we have of like distributed computing. The first one is like network is reliable, that no matter like if we make a request, like it's gonna happen eventually, and that latency is zero. Latency is zero, like it can mean multiple things, like for example that uh, uh, like if latency is zero, we'll not need some like message queue, because like we don't need to like store it somewhere before we reach the like another component of the distributed system. So that's another wrong assumption. And bandwidth is infinite, because like network can congest too, and network is secure, like it's not discussed in the book, I think, but still is another fallacy we have. And topology doesn't change. So I don't think like this is much important right now because of the relevant of like Consul, Eureka, like even you or like even like Kubernetes makes the topology change
There is generally a service discovery
yeah.
thing which we rely. Okay.
Okay, yeah. So there's one administrator. Yeah, this then there's if there's a multiple administrator, then there can be some collision between the some the, like both two different administrator can like ask for two different kind of thing, and there can be some collision, and both of them have the highest level of privilege. So there is another problem. Transport cost is zero, so like it always gonna take some sort of bandwidth or like CPU, RAM, or anything. And network is homogeneous. I'm not much sure about this. Okay, so I congested like 6 to 7 pages into this small part. So I'll go through I'll go through them. Okay, so first one is the clocks and time. Like clocks is not like the problem is that clock is not synchronized across all the nodes. So this might one example can be so he didn't give like much example about this, but he said that there can be many problems if we don't take consideration of this. Like for example, he said that about time series data. So if there's two node, one node is communicating with another node, and the second node, the destination node of the some request, so they are relying on the like time information on the timestamp that is coming from the first node. So there can be some issue, like some problem can arise from the timestamp that the destination node is getting from the source node. So he said that like if we combine like this kind of dependency with what is the word with like latency is zero and processing is instantaneous, then there can be many different problems. He didn't elaborate on this, but we can think like that there can be if the second node or the destination node is relying on some timestamp from the first node, the multiple thing can be like synchronization might not happen, and message ordering is another thing that if we rely on the first node's timestamp, there can be some issue. Okay, so after that there's like processing takes no time. So processing takes no time is that like one like really good example can be that like uh, if the what is the word so node like node 1 is pushing lots of messages to the second node, but uh, the node second node is like overwhelmed with processing all the requests it is getting. So if like so all the every new request it's receiving, but it's going to be on backlog, and it there's like two things. One thing is like how fast it can process data. Another is that like how the queue size. So if the processing if it cannot like process fast enough, the queue is going to get full, and there can be like out of memory issue, or the node can fail, like lots of things can happen. So the fix of this thing is like using back pressure. Back pressure is that it's like when the producer is like publishing at a rate faster than the consumer can process them. That is the like at that time like it can back pressure can stop it, like from the second node it can send back some command or some information to the so that like producer will slow down. Okay, so yeah, uh, uh, there's like a few things that we already know, like it helps like these decoupling or pipelining with message queue, and message queue can absorb small like short time bars, like we already know about this. Okay, so there's another thing, state consistency. So okay, so state consistency is that like we have the assumptions that we have the assumptions that uh, like for example in Cassandra there can be like like all the different nodes there. So there's going to be consistency of the like the storage the storage of the like whatever any of the node is storing, all the other node has the same sort of data. So but that is not always the case. So there was two examples he has given. So the two bugs, so one is like Apache Cassandra bug. So it was caused because like schema validation, like schema sorry whenever schema changes, it takes little bit of time to propagate throughout all the nodes in the cluster. But that assumption, like that wasn't taken in consideration when the Apache like Cassandra was built. So if somebody else is like reading the data while the schema like the schema change is propagating throughout all the server, like there like the user will read some like false memory, or the wrong information. So that is one of the problem. And another bug is like divergent view of the ring. He provides some link that doesn't take to nowhere. So if any of the nodes assumes that other node holds the data records, or like or like some sort of input, sorry, some sort of like value, but other nodes has a different view of the cluster. So I mean like there's no consistency. So like reading and writing data will create like more inconsistency, and like there can be some problem of like for example that fast node have some data about something, it has some key value, but it's looking for so it has some key, but it's looking for the value for that key. So it's requesting for that thing across like different part of the node, but they don't have that value or they don't have that key. So like there's a mismatch between two different nodes, like so it will get an empty response, so even though like it's not supposed to have that empty response. So that is the state consistency problem. Okay, so there's like two solution to this. Like one is conflict resolution. So conflict resolution is that uh, uh, so conflict resolution, like he didn't elaborate it, but like it is to be able to detect the divert state. So I don't know how how this is implemented, but through
Yeah,
like
we use this CRDT for this
okay, okay,
conflict resolving data types. Yeah.
okay, conflict
So
resolution, yeah.
if any change happens in one node, we actually send the delta, which is a change. We broadcast that to the other nodes, and
Okay,
then when we get all the changes, we add up all those changes. So it doesn't matter in what order you apply the changes, like you do +2 -2, or you do -2 +2. We will always get to the same result, basically.
okay, some sort of like it's close to event sourcing. Then I guess I forgot the word. Like is CRDT like related to like Wasm or something else? I forgot. Like I think the Vercels creator did this. I have
No,
mentioned
no,
it.
no. No, no. It's just a concept. I
No,
mean,
no, no. But
you
it was
just send.
based on somewhere, like some specific technology. I forgot. Uh, like it was this protocol was created for like this sort of data structure was created for one particular specialized task. I forgot that thing. Oh, I remember Figma. He developed this
Yeah,
thing
yeah,
too for
yeah. I
Figma. Yeah,
mean, basically for any like in Google Docs as well. I think like any
yeah,
kind of thing where we have multiple masters,
yeah. Okay,
and you need to sync between multiple masters. Yeah.
okay,
Okay. Okay. You can continue.
yeah. Okay. So there's another solution to this is like read time data repair. So it's uh like bringing like making all the nodes sync, like all the replicas sync at the time of like reads. Like if like there's like multiple like for example one node request for some value, and it's getting two different results from two different places. So there will be a force sync between all the nodes, but he didn't like give any details, like that was it. Okay, so another is like local and remote execution. Okay, so this one like he didn't elaborate, but I wish he did. But he mentioned few papers over there, so I'll try to go through them. So I like this one, like the way he phrased this thing. So I think Hussein Nasser said the same thing. Like he was saying, like Hussein Nasser, like he says this again and again, that hiding complexity behind an API might be like dangerous. So so the example they give so what Hussein Nasser says is that like if something is like really complex, then you need to like expose some of, like if that complexity cannot be taken care of, then some of that complexity need to be exposed to the end user, so that they can manipulate that, or like they can use the like what is the word, control some of the complexity from the user end if that is need to be done. uh, so the example in the book was given is that think like you have two data set sorry two database. So you have two different database, but one of them remote, one of them local. So I think by local he means like close to the node, and remote means like far away in different region. So if you have same interface to connect with both of the database, there can be lots of issues. So one example he gave that like that local database and the remote database, uh, both of them will have like different response time. So that can create many issues, that if the user is not handling that thing, one of the problem that can arise, like I'm guessing from the way he wrote that, that uh, in local database, uh, sorry, in if some response or if some request came from your remote database, you need to give that fast like a higher priority, because because there's some traveling delay, so that request must like might fail if he doesn't process it process it in priority basis. And if we give priority to the like local database because of like fast out or the this kind of priority basis, then the remote database request might fail. Okay, so this is the example he gave. So there's another thing is like node failure. So node failure can be solved by heartbeat protocols. Like heartbeat protocols, I think you know about it already. Like this can be like for a WebSocket is like ping pong. So one of them will give ping pong out. Like on Kubernetes, this can be like a readiness probe. Like after some certain amount of time, some certain API will be hit to check if the application is running or not. And there can be some failure detector, so he didn't elaborate on this. And network partition and partial failure, so this is fault tolerance. So he said lots of things, but I'm not like I guess he could yeah. So there can be like in like what he said basically is that in a highly available system there can be so many edge cases. This is a really hard problem. So what we can do, we can only do things that like we can simulate all the like chaos that is possible in a distributed system. Like we can simulate bit rot. He didn't say like what this is. I'm guessing some packet corruptions at the network. So we can increase simulating the increase of latency, like different clocks across the system, and magnifying relative processing speed across different like replicas. So by simulating this kind of thing, like we can be sure that our distributed system can handle this kind of like network partitions. Okay, so another thing is like
Okay, well,
sorry.
this was not very understandable. I mean, what
Okay,
do you
okay.
mean by diverging clocks? Or, I mean,
Yeah,
yeah, I
yeah.
mean, just
Diverging
the thing
clock
is,
means
like,
is that like
it
what I
would be
told you
nice if
earlier,
we went into the detail. Hmm?
different like the clock times, like clock time is will be different across like different nodes.
Okay, because
They will
I
not be
guess like
synchronized.
one node failed and then it came up and then it just got unsynchronized, maybe because of that.
Okay, like so think this way, like so etcd, like they are like always synchronizing. So whenever
Hmm.
like if you like there can be sometime issue that like if one of the node has some sort of problem, etcd will sorry no, some sort of like that clock is not like in like clock is not matching their time with other nodes. So the etcd will fail, like because like they have to be always like running synchronized. So and like many different component, like I will talk about it little later, that like especially if this is consensus based, then like if different time will like break the whole system. But uh, many component distributed system is like dependent on that uh, clocks are synchronous across all the nodes. So this like if you want to make it fault tolerance, then you need to try this with diverse clock system. Like all the things that can go wrong in a distributed system, you need to try that. Like for example, increasing latency between different nodes, or like setting different clock times, or like the processing speed, like slowing down one of the nodes processing speed like artificially. That can be one of the problems. So do you have any questions about this?
No, I understand. So we will intentionally use like unsynchronized clocks and see how the system behaves and
Yeah,
make it resistant against
yeah.
that. Okay, okay.
Okay, so cascading failures is that like this can this is like one of the failure like cascading over like other part of the distributed system. So this can be that so one of the example he gave that like, so this can happen from this can happen out of nowhere. Like for example, because of like some of the node can be like turn off, or like it can be like rebooted for some reason, like for maybe some network kernel update or some important patch update. So when it comes back online, it's like like it's PRs, or it can be like message queue that can push all the, or like all the request, or all the things the uh, just restarted node missed. So there will be so much, like the network resource will be exhausted, and the processing or the memory might be like exhausted of the like now restarted node. So, and because this node fails, it can create like issue on like other defined nodes too. So one of the solution is that like circuit breaker. So back of timer is that like some back of timer on the client. So whenever a fail happens, the client makes a request, a fail happens, it's not gonna request or like immediately. So instead of like immediately, it's gonna like request after 2 seconds. If it fails, it's gonna request after 4 seconds, or so and so on. So, and I forgot about the validation part. Mm, Let me read some part of the book. Um, okay, do I need to elaborate on the circuit breaker patterns, or
No, no.
yeah? Okay.
I know this about sir. Pranit, do you also know, or
Yeah. I
you
work in
can
HTL,
explain it?
so yeah, I know. Okay, I missed the validation part. I will try to talk about it like next day. I forgot about the coordination part too. I will
Wait,
talk about
wait.
it. Yeah.
No, I was asking Pranit that whether you know about circuit breakers or
I know,
not,
I know.
or
I
you
work
can
with
explain
HTL.
a bit.
Yeah.
No, 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 not to you, to Pranit. Okay, he knows about it. Okay, yeah, we
Like
can
you're
continue.
talking, communicating on the like chat. Oh, okay. I thought he was responding. Okay, I didn't know that.
Okay,
Okay,
yeah.
if
So you can
you,
move to the next
yeah.
slide.
So the question you asked earlier. So this is somewhat relevant over here. If you'll, okay, so before that there's some terminology on there, so I didn't put in here, like there's some links is that like network, like so uh like fair loss link. There was some like terminologies there, like fair loss, finite duplication, send messages won't be delivered infinitely many times. So I didn't went through those terminology, like uh so like message retransmit, this is like retry, but uh like 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 there was some terminology there, like stubborn link and things like that. Okay, so then there's like message order. So so I guess you know about like idempotency, right?
Hmm.
So like, so message ordering is like, sorry, message ordering, and another is like exactly once delivery. This is okay, I didn't add the slide, but so this is like a really hard problem. So this is such a hard problem that it's not actually possible to like what is the word, it's not 100% like what is the word, uh, it's not
Yeah, I mean,
possible
we
to,
can
yeah.
never 100% guarantee that the message will be delivered
Yeah, the message
exactly
delivered.
once.
So
Yeah.
there's a famous
Mhm.
problem called like two generals problem. Are you both of you like aware of that two generals problem?
No, I haven't heard
Okay,
about that.
okay.
Can you
So
explain?
yeah. So so this is like one exactly once delivery, or like the ordering problem. This is the idea actually comes from the two generals problem. It's from the 1970 or 1980. I forgot. So the
Hmm.
like, so on the book they just give the problem statement, they didn't give the solutions, but like I'll try to go through both of them. So into like, think of like there's a castle, so there's like two generals, they're on the two defense like far away from each other, but they're going to like attack the castle. So they will only succeed if both of the general attack at the same time, and they like so, but if they don't attack at the same time, they'll fail. So they want to be like, they want to make some coordination, so that like they both of them are sure that like they're going to like attack at the same time. So what will happen is that like if fast like what is the word fast general is send some message to the second general that hey like this is the time we want to we want to like what is the word we want to attack. So the second general will second like if the second general receive the message, they're going to send some acknowledgement back to the fast general. Okay, so when the fast channel receive the message, so he's going to send he need to send the acknowledgement to the second channel too, because the second channel doesn't know that the fast channel agreed with it. Okay, so this is the like sorry, let me repeat again. The second channel send the acknowledgement, but the second channel doesn't know the fast channel fast channel received his acknowledgement. So the fast general need to have sent another messenger that he has received the acknowledgement. So this will go so and so on. Like there's no way to like make sure that like that any of like what is that, because like at any moment like any of the messenger can be intercepted by the like the enemy spies, and the other person will not be know that like okay the other person got the acknowledgement or are we on the same page or whatnot. So even though like it can go through infinite times, like but we'll never know. So this problem is not solvable. So there's two solution to this, like two approach to this. So what the TCP does, that before they need to know uh, how reliable the communication is. So uh, how reliable the communication is. So in case of like general, we can say that general doesn't care that how many of his messenger dies. So fast general will send 100 messenger at the same time. So the second like each of the messenger will have some like number on them, like number 1 2 300 like on their message. So they'll send the messengers. So the second general will receive the messages, and he will send back the acknowledgement for that, like all the. So from the amount of acknowledgement the fast general receive, from that he can guess how reliable or how like reliable the messengers are to deliver the message. From that he will get an estimate, and he will send a proper amount of like messenger. And if he like the same way, the second general will like get some idea that how reliable the messengers are, because like he knows that 100 messenger will be sent and how many of them he got. So according to like he will send back like proper amount of messengers to the fast channel too. So this is the this is so this approach is taken when the packet sending cost is not like is trivial, or it's not expensive. But another thing can be I forgot like half of but what I remember is that like uh, the second solution is that like if you have like you need to have time, like if you have enough time, then you can use this solution. So this will be based on the fact the other general will not send any like what is the word any message. So this is like that fast channel will send some message, send a messenger. If the second channel receive it, they'll send an acknowledgement. So after that the second channel will wait. So if the fast channel doesn't send anything back, that means he has received the message. So did you get this part or?
I kind of understood, but can you give an example, like in a real world view with the
like
microservices where we use
this is
this?
like TCP. Like TCP works this way.
Okay. Ha ha
Like
ha, because there is a three-way communication, that's why.
yeah. So like
Three-way handshake.
there's a
But
flow.
other than TCP in general microservices, do we use this? I don't think so.
Yeah, like for example that what is the so there was a problem in Uber Uber food, I think Uber food in UK.
Mm-hmm.
So some of the people have like ordered something, they saw that their order didn't register, so they ordered again, so they got two orders. So what happened was that like idempotency wasn't implemented, but okay, no, so sorry, that is idempotency, this is not about this, but uh, like but at the same time, like if no, yeah, that doesn't happen, but like to make something reliable is the if okay, no, I, for example, we only make one request, right? So that like the channel, how reliable the channel is, that is handled on the like TCP connection layer, right? So we don't have to think about this, like, right?
Okay.
Because like the TCP will
Okay.
handle that part, like that difficult
Yeah, I
part.
mean,
Yeah,
yeah, I understand. With the TCP, we have this thing three-way handshake where like we send a connection initiation request,
yeah.
and then we get back an acknowledgement, and then we send back an acknowledgement. So there's a three-way. But other than that, I haven't seen this like three-way thing happening anywhere else. That's why I asked. But okay, I mean TCP is a fine enough example.
Yeah,
Okay, so
because
we
like
can
most
move
of the
ahead.
microservices like on works on like layer 4, like not like not actually on layer 4, but because like we don't implement like TCP on like microservice, right? Because we already
Mm-hmm.
have something
Mm-hmm.
reliable, so we're working on that channel. Yeah, so
Mm-hmm.
okay, so wait, okay, so after that comes the like FLP impossibility. So FLP impossibility is that like is a consensus like protocol, like sorry,
Wait, I think we already got through this FLP
no,
impossibility.
we didn't.
Okay.
Okay, so FLP is like name of like three different author. So a consensus protocol describes a system that, given multiple processes starting at initial state, brings all of the processes to decision state. Like this is the definition kind of thing he like written. It doesn't make much sense, but so like so there's like three properties. Like a consensus protocol has three properties.
Mm.
So first one is like agreement that okay, unanimous decision among all the participants. So
Okay.
if there's like if there's like actually like I saw like for example etcd, like if some of them disagree, like majority rules will work. So and there's like validity, like this part I'm not much sure about this. So what he said about in the book is that like process should always decide on some process should not all like process should not like decide on some predefined default value. So what you're saying that like if agreed value has to like the agreement, like it has to uh, p- like the agreed value has to be proposed by one of the participants, like think of etcd that so then he said, which means that the system should not just come up with the value. So I'm not much sure about this, so I'm thinking I'm guessing like there's some deterministic way to come up with this. There's not some like sets like constant values stored on the node or something. I'm not sure about this. Okay, so and the last one is
Okay.
termination, is that an agreement is final only if there are no process that did not reach the decision state. Okay,
Okay.
so there's some systems synchrony about it, but like okay, there's some few paper he mentioned. So the paper shows that uh, these three like a concept, like this is the first three like this like assumptions, and this is like somewhat right. I'm guessing that like no, I think they proved it that for a consensus protocol to be correct, they need to have these three properties. And then he showed that we cannot always reach consensus in an asynchronous system in bounded time. So like what this means is that like like if this is asynchronous system, then like the consensus like consensus can take like infinite time. So the on like so like that is the problem. So he didn't talk about asynchronous system much, but what he said later is that like if we make the system like synchronous, the whole system synchronous, much of the like most of the problem like goes away, so we can work much easier with that. Okay.
By synchronous system, you mean like
like for
I send a request and I immediately get the response. Or what?
no, uh, so I think you can take with that too, because like ETCD like actually measures like how, what is the like the bounded time, like like because like the way ETCD works is that like if the request or response, whatever it is, if it takes
Hmm.
like, sorry, response takes like response crosses a certain threshold, then like there can be it will handle that like fail, like connection failure in certain way. So like but like if it is asynchronous means that like it can wait indefinitely, right? So that's why like
Yeah.
hello, yeah, do you have any question, like do you not agree with this, that if some request is asynchronous, the it can go for indefinitely, right?
Yeah.
Yeah,
Or
so
I don't know, maybe it's like fire and forget, and then when like the
yeah,
response
then that
can
is
come at
asynchronous. Yeah,
whatever later.
yes, yeah, so that is asynchronous. So for that there can be some
Hmm.
like
But
different
it
yeah.
would have, it would have been nice if we had like a concrete example or something.
Yeah, so like so what he said is that like in asynchronous, like there's some problem that arises with asynchronous system, that creates this kind of like, so that we cannot reach the consensus, is that the relative speed of different processes, then like the guaranteed message, that's another thing. mm,
Hmm.
uh, so these are the two things he talked about. So yeah, so there's like
Okay.
multiple chapters about like consensus and like the asynchronous like consensus based algorithm. There's Paxos, I think. There's RAF. So I think we'll
Hmm.
be able to talk about that
Hmm.
later. So after that, there's like failure model. So there's like different way to handle failures. So he talked about like multiple things here. So on the crash false, I think this is goes close to Kubernetes model. Is that like it's like we don't assume the like it is impossible for the process to recover. So whenever some crash happens, the process will like auto restart, like just like Kubernetes. So the
Okay.
omission false, I think like the definition he gave, like there's like so many things in there, like it's like discombobulated, like I didn't like the way he said that, but so I'm just talking about the one example he gave. So he gives like so he said that this can happen on some like fault tolerances, like when some network partition happened, or like many things that can happen, that like for example the example I give for Apache Cassandra, that maybe like
Hmm.
some part of the system might not be visible to other part of the system, that someone requested for some, like Apache Cassandra one node requested for some record value against some key, but that node doesn't know about the existence of that key or value, so it will return an empty response. So he gives like lots of examples. So the omission fault is that like the example that I liked is that a process like process can omission or like skip some of the like steps of execution that is supposed to be. So
Okay.
uh, or so when that happens, that what is the word, omission fault happens. So one of the example is like good example is that like for example someone send a request,
Hmm.
and it didn't like it didn't get any like like what is the word, response. So if it doesn't
Hmm.
get any response, it's supposed to retry or like other things supposed to do, but it just like ignored all that responsibility and it just moved forward. So that is omission fault. So there's like arbitrary fault,
Okay.
it's another name is like Bayesian fault. So this is the hardest one to recover from.
What
So
is the other name? Byzantium.
Byzantine, sorry,
Ah,
Byzantine.
yeah, yeah, because there is some like Byzantine consensus protocol or something
Yes,
that I read.
yes,
Okay.
yes, Byzantine consensus protocol. So here like the way it happens is that like uh, so, there in consensus algorithm, like there can be some like it can contradict the algorithm in such a way, like for example that uh, uh, like not just consensus algorithm in everywhere, but one example is that like in a consensus algorithm, like for example that the leader need to elect, like they need to elect some leader. So there's like 5 nodes. So number
Hmm.
one said number one wanted to select number seven as elected no. So that
Hmm.
is like that is some like so the algorithm doesn't know how to like work with it. I think like my what I said is might be wrong because like that might not be an issue, but I can say like instead of number seven it might send a string and so that can be a problem. So there's no way to handle this thing. So arbitrary failures like there can be like random things like there's no way to handle this thing. So this is
Okay.
happens on the like extremely like fault tolerant system like there can be no mistake like airspace industry like airplane or space like control system kind of the control theory kind of system. So there's the
Okay.
handling failure is that God. Oh wait, I forgot to write this part. I think I wrote it somewhere else. Okay, so and
Okay, that's fine. But then almost we are at the end, right? Like, uh,
this is the chapter.
did
This is the one chapter. Yeah. So repeat.
okay, okay. Yeah, I mean, we can end for today, I guess. But I mean, I think it would have been better if you included like concrete examples here.
But the book doesn't
I
have much concrete example. That's the problem. Okay, let me
okay,
show you.